use, talk about some of the terms that we use, what they mean, and how it affects propagation. Then right at the end, I'm going to take a look at 2 propagation prediction programs that you may find useful. So let's have a start. So, oh, that's good. Right. So currently the, let me just go back one. I thought there was another slide. No, there isn't. Okay. Currently, in terms of GB2RS, there's a number of us who produce it. I look after the HF part, and Jim G0KYA looks after the sporadic E part, and both Jim and John G4BAO do the HF and VHF part as well. So they look at tropospheric propagation there. And then finally on EME, that's Earth, Moon, Earth, Aurora, Meteor, Scatter, that's John and Sam G4DDK. So, I mean, between, how many is that? Is that 3, 4, 5 of us, I think? 4 or 5 of us, there's quite a lot of experience there. And we don't generally argue too much, so that's okay. And it's put together on Wednesday afternoons usually, and checked on Thursdays. Then it has to be uploaded by Thursday evening, so it can be put together onto the RSGB's GB2RS on Friday. So when we talk about what's happening in the next week, actually we're producing it 3 or 4 days before the next week even starts. So sometimes we get it wrong, and but that's just one of those things, I'm afraid. But anyway, let's go forward. So what we're going to look at tonight, we're going to talk about solar flux index and smooth sunspot numbers. We're going to look at K, KP, A, and AP indices, what they are and why we use them. Talk about the solar wind, which is actually very important, both its speed and the direction of its BZ. And we'll talk about what the BZ is and why that's important a little bit later on. Then we'll have a look at critical frequency and maximum usable frequencies. What are they and how do we use them? And then, as I said, we'll look at a couple of prediction programs, and I'll take you through how you can use those to do your propagation predictions. But in terms of GB,
Yes, Steve, you've gone again.
Steve, your audio's gone. Yeah.
Right.
Ah, that's it.
Is my audio back?
Yes.
Oh, that's just weird. I don't know why it's doing that. Where did we get to? So yes, so they said we could broadcast could be made on Sunday mornings in 3.5 to 3.8 megahertz band, or megacycles band. I like that. With telephony and or telegraphy. And 7 megs came on board in 1956. Now, the propagation segment of GB2RS was produced by Nichols G0KYA and Martin G3USF for more than 20 years. And talking to both of them, I actually met Neil at the Newark Hamfest again the other day. I hadn't seen him for about 5 or 6 years. And Neil would freely admit he was interested in the sun, but he wasn't interested in propagation. He understood how the sun worked, but he wasn't really bothered about propagation whatsoever. And so the propagation segment on GB2RS was very much about the sun, what the sun was doing, and very little about propagation. So when I took it over, I'd said, right, we've got to change this so it's of more relevance to radio hams. And that's what we've been doing for about the past, I think it's 5 years now. And we don't get much feedback, actually. Don't get much feedback as to whether people like it or it's useful or not useful. So any feedback you can give me would be good. And as I said before, it used to be about the solar factual data and the solar forecast, and it still contains a lot of solar factual data and solar forecast, but we try and say how that actually what that actually means for propagation as well. If my audio goes, you'll just have to shout, I think, and I'll kick it off again. Right, so where do we start with? Well, we need to know the solar flux index and K indices. And so the starting point for me, anyway, is these two URLs here. One looking at the daily sunspot data and one looking at the daily geomagnetic data. And these are all freely available from NOAA.gov. I'll leave the URL on there if anyone wants to make a note of it. But this is where we start, at least. This is what's been happening, what happened in the last 30 days. It doesn't really tell us much about what's going to happen in the future, but we'll come to that in a minute. So that's where we start in terms of, well, what was the sun doing last week? And were there any flares? As you can see here, we have a solar flare and X-ray flare information there, and how many regions there have been, the sunspot number, and we'll talk about what the sunspot number and solar flux are in a second. And then, as I said, we look at the geomagnetic data as well. So this was a shot from today. This is the sun as of today. Not that I would have seen it. The weather up here has been lousy. But this was taken by, or taken off the solarham.com website. And as you can see, we've got 3 major sunspot groups coming in, and one just about to leave. The rotation is left to right, so that one is
Your audio is gone again, Steve. Your audio is gone.
right. Let's try that. Is that any better?
Yeah, much better. Perfect.
That's weird. I really don't understand why it's doing that. Okay, right. Let me get back to where we were. Good. So you now got the screen back again? Good, thanks. Good. So let's talk about the solar flux index first of all. The solar flux index is the strength of the radio signals coming off the sun at a wavelength of 10.7 centimeters or 2800 megahertz. It never goes lower than about 60 and can go as high as about 300. And for 10 meters to open up, the solar flux index has to be really in excess of 100. And high values generally indicate there is sufficient ionization to support long distance communication at higher than normal frequencies. But something I have to make clear here, the solar flux index, the strength of the signals coming off the sun at 10.7 centimeters has got nothing to do with ionizing the ionosphere. It's what we call a proxy for it. The strength of the solar flux at 10.7 centimeters roughly equals what's going on at ultraviolet. So we measure the strength at 2800 megahertz, and that kind of tends to tell us what's happening at ultraviolet. The reason for all this is that we can't measure the ultraviolet output from the sun on the Earth because the ionosphere, the ionosphere basically absorbs it. So this is the only way we can actually do it. And somebody said to me recently, well, why are we still doing this now that we've got spacecraft? Why do we need to do this? Why don't we just measure it in space? And I think this is just one of those historical things that it's been going on for so long now that we've continued with it. But as I said, so the solar flux index never goes lower than about 60 and can go as high as about 300. I think today it was about 115. So it gives you some idea of where we are in terms of how good is it. Not brilliant, but not bad. An alternative way of looking at solar activity is to look at the number of sunspots there are. And when we talk about the sunspot number, People think that's how many sunspots are. There isn't actually. Basically, we score 10 points for each sunspot group and 1 for each sunspot. So 1 sunspot in 1 sunspot group gives us a sunspot number of 11. And if we had 3 sunspots that were well separated, that would be 3 groups. So that's 10 plus 10 plus 10, and 1 plus 1 plus 1 for each of the sunspots. So that gives us 33. So you can see that you can go from 0 to quite high sunspot numbers quite quickly with very little happening. So you can go from 0 to 33, and all you've really got is 3 separate sunspots. So that's one of the things. And sometimes people say, why then do you bother with sunspot numbers or solar flux? Why do we bother with the two? And I think again it's just historical. Obviously in
You're breaking up again, Steve.
Yeah, you've got a.
one, two.
Gotcha.
Yeah, weird. Okay, let's get back to the presentation. So as I said, the lowest value you can get is 0, which is a completely spotless sun, and the highest can be as high as 286, which is solar cycle 19. But I think the thing to remember is that when we say 286 or sunspot number of 286, that doesn't mean that there are 286 sunspots. It means that, you know, there are groups and you're getting 10 for each group. So it could be 286. It may be there's maybe 50 sunspots, but the way it works, you know, if there's 50 sunspots and they're all in separate groups, that would give you a high solar sunspot number of something like 59 or so. But I think that's just worth pointing out. Okay, now one of the sources of information we use is solarham.net, which I thoroughly recommend that you all bookmark immediately. Solarham.net is produced by VE3EN and has an awful lot of information on it. And it's the single one place to go for all your solar data. So I mean, just talking you through this then, so we've got the sun in visible light up here on the left. Got a magnetogram here, which shows us also the sunspot areas you can see. We've got the solar flux index and the sunspot number here. Then we come across to space weather data. So we've got X-rays coming off the sun. So this tells us when there's been solar flares, and protons. If we get a lot of protons coming off the sun, we can get a proton event. So that shows you the proton flux. And finally, this little graphic here shows you the K index, and we'll talk about the K index later as well. In addition to this, it's got lots and lots of other stuff you can look at. The sun in X-ray for coronal holes, and lots of information. He does a daily write-up as well to explain what's going on. So it's worth bookmarking. It really is, because some fantastic information on there. So geomagnetic disturbances, that's the first thing I want to talk about then. So the sun is constantly losing matter or plasma off its surface, and we call this the solar wind. And at times this wind can be more ferocious than others in terms of its density and speed. When we're talking about a solar wind, you may think of the wind being about sort of 50 miles an hour or 50 kilometers per hour. The average solar wind speed is something like 450 to 500 kilometers per second. So not per hour, per second, which is hard to get your head around, but that's an incredibly fast solar wind. And you can actually get other information about this, that the solar wind, this is why it can damage satellites, because if you bombard a satellite with ions at 600 kilometers per second, you can imagine that it can do quite a bit of damage, which is why some satellites end up with what we call single event upsets when they don't work and have to be rebooted. But anyway, that's the solar wind. And the solar wind can come from coronal holes on the sun. We'll look at coronal holes in a minute, or from coronal mass ejections. So all this stuff is flying off the sun at a very, very fast rate of knots as well. And we're not talking about just a small solar wind. It can be the size of the Earth. It can be massive. Millions of tons of matter is being lost, or plasma is being lost, every day. Okay, now something about plasma is that it can have a frozen-in magnetic field. A moving plasma can have a magnetic field, and with that magnetic field, it can either be basically pointing north or south. And if it points south, we say it more easily couples with the Earth's magnetic field. So it's a bit like bar magnets. If you think of bar magnet north and south, the north and south would match up and connect quite nicely. So this plasma coming off the sun has this frozen-in magnetic field. And if that frozen-in magnetic field is pointing south, it more easily couples with the Earth and gives us problems. And when this happens, we find that the plasma basically distorts the Earth's magnetic field and triggers aurora. It gets channeled towards the poles and triggers aurora. So you could have a fast solar wind, but its magnetic field was pointing north, and it would probably have very little effect on the Earth. Or you could have a solar wind, fast solar wind, pointing south, and that would more easily couple to the Earth's magnetic field and cause big problems. So this is the first thing, was we may know that there is a strong solar wind, but we don't know until it actually hits the first spacecraft in space, whether it's north facing or south facing. So this is why sometimes we get it wrong in terms of what's going to happen. Now, coronal holes, I just mentioned the term earlier. This is the sun in visible light on the left, and in X-ray or far ultraviolet or X-ray on the right. Now these holes here, these dark areas, are lower energy parts of the sun with open magnetic field lines. So these magnetic field lines are no longer contained in the sun, which allows the plasma to pour out. So generally, these coronal holes are not good news for us, not good news at all. And we have to keep an eye on where these things are and what problems they're going to cause. We'll look at that in a sec. They were first identified in Skylab, or from Skylab, which is the first time that anybody pointed a camera that was visible or was looking in the X-ray region or extreme ultraviolet region, and suddenly saw these dark areas and thought, what the hell are they? So they've not been known about for that many years, but they do play a major part in solar predictions. So, and I think the thing is, if you look at the left-hand one there, there is no indication whatsoever of the coronal holes on there, just the sunspots. So this is why it's so important that we keep an eye on coronal holes as well. And the Solar Dynamics Observatory is the spacecraft that's being used here to look at it. So just to recap then, so coronal holes are areas of the sun with lower energy and open magnetic field lines. And they're responsible for adding to the high-speed solar wind, and they can cause geomagnetic disturbances. They should be less prevalent as we head up towards maximum, although we've had quite a few, but will likely increase as we head towards minimum. So once we get past solar maximum, the instances of coronal holes may increase dramatically. And this, just to show you, this is the effect of a coronal hole. If we look at the image on the left there, we see that the part marked 34, that's been rotating from left to right. And you can see that it's now gone past the point where it's pointing at the Earth. And this was the effect it had. So the K index or KP index went up to 5 due to that coronal hole. So this is why it's so important we keep an eye on coronal holes. Basically, when the coronal hole is dead center there, it's going to be a couple of days before it impacts us. Or to make it a little bit more of a scientific calculation, if we do the sums on this, you can see that the average speed of the CME or solar wind is 400 to 800 kilometers per second. And therefore, it's about 2.1 to 4.3 days, depending on how fast this solar wind is. So when I look at these things, and if I see a coronal hole and it's dead center in the screen, then you could usually say that 2 days after that, roughly 2 days after that, that's when we'll see the KP index go up, and it will have a bad effect on us. Now, solar flares and coronal mass ejections, you'll see there that there's a lovely photograph of a CME. We've got plasma coming off the sun, and you'll see that the Earth is to scale there, which is a tiny dot in comparison to the CME. The CME is massive. So if the sun unleashes a coronal mass ejection at us, and these things are usually linked with solar flares, not always, but usually, if you have a bad solar flare, you sometimes, and well, generally can have a coronal mass ejection at the same time. Not always, you can have a solar flare without a CME, but if you get one of these things coming off, again, the speed of this is 600 kilometers per second, very fast, and millions of tons or billions of tons of matter coming towards Earth. And as you can see, you know, Earth to scale, that's going to completely drown us, to be honest, with the solar flare or with the coronal mass ejection. And we measure solar flares with a scale. These are some X-class solar flares here and here, and an M-class solar flare here. So an X1 class solar flare is about as bad as it gets, which is up here somewhere. But basically, if we look at the X-ray flux, this is on solarhammer.com as well. And this shows you these solar flares as they're happening in virtually real time. So not good at all. The main component of solar flares is a massive surge of X-rays. I did some calculations just to see just how much energy is in one of these things. And as you can see, the atom bomb they dropped on Hiroshima released about 10 to the 13 joules of energy. And the world's biggest atomic bomb was 10 to the 17 joules of energy. And an average CME is between 10 to the 20 and 10 to the 25 joules of energy. So that's at least 1,000, if not 100,000 times more powerful than the biggest bomb that we could let off on Earth. So you get some idea of just how much power is coming out of these things. And this also shows you why, when they're planning spacewalks, they really don't want to have it when we know there's going to be an awful lot of solar flares and CMEs. You really don't want to have astronauts being impacted by this stuff. Okay, so what does a solar flare do? Well, the X-rays from a solar flare impact the ionosphere and burrow right down to the D layer and cause absorption. And absorption at the lower frequencies is the highest. So this could cause a sudden ionospheric disturbance, maybe on 40 meters or 20 meters. May not affect 10 meters much at all. But the important thing to say about this is that it is on the sunlight side of the Earth. So if you have a solar flare during the day, it may just sound like the band's just been switched off immediately. And then it will recover over a period of maybe 20 minutes or 2 hours, depending on how bad the solar flare was. And this shows you the likely attenuation of the signals. As I said, the lower signals are attenuated more than high frequency signals. So you will notice the effects of a solar flare on 40 meters, 30 meters, 20 meters, say, more than you would maybe on 10. But you don't get much notice of getting a solar flare. It's either there or it isn't. I mean, the Carrington event back in the 1800s, I think it was, wasn't it? He saw a solar flare. He was an observer and observed the solar flare, and then noticed that we had aurora 2 days later and thought there must be a connection. Well, that's obviously was the connection. They had a solar flare, had a CME at the same time, and 2 days later the plasma hit the Earth. So this is why it was called the Carrington event. And it was a massive, massive solar flare and massive CME. And everyone's been waiting for the big one to hit the Earth ever since. And unsettled geomagnetic conditions are typical at this point in the cycle. Actually, it will get worse once we get over the peak. but this was a typical day in 2003 when you can see the K index there has gone up to 9. When was that, 2 days running, and really didn't recover until, well, maybe into November, and this was October the 29th. So this would have a serious effect on the ionosphere. Wouldn't do satellites much good either, but this would, really badly affect the ionosphere. So why do we measure this K index, and what's the KP index? Well, the K index is a measure from magnetometers on the impact of plasma on the Earth's magnetic field. And what we find is that this plasma, as it hits the Earth's magnetic field, it will cause magnetometers to distort. And the amount of distortion you get on the magnetometer tells us how much we're being impacted. And we have a scale of 0 to 9. It's a logarithmic scale. So if you have a K index of 9 or KP index of 9, I'll get what the P is in a minute. A KP index of 9 is a massive, massive disturbance. The KP index of 9 is the sort of thing that would give you aurora down at, British levels. I think you would see maybe even further south than that. Recently, I think the worst we've seen is maybe 5 or 6, but I wouldn't be surprised if we see a 9 event sometime in the next 10 years, maybe once we get past solar maximum, which is 2026 or thereabouts. And just one other thing there, it says KP planetary. The distortion is measured around the world. Fredericksburg in America is one. It's a place in Alaska where it's measured. And what they do is they average all the measurements out from around the world to give a planetary K index. So KP is a planetary K index of this distortion around the world. So just to recap then, so this is data plasma impact to the Earth's magnetic field and causing this disturbance to the Earth's magnetic field, and we can measure that with magnetometers. And the more the disturbance, the greater it is disturbed, the more likelihood we're going to get auroral events, and it has an impact on communications at the same time. The A index is another way of measuring the distortion, but there's just one problem. Where the K index is a logarithmic scale, the A index isn't. So for instance here, a KP index of 9 is equivalent to about an A index of 400. Now, the only thing is the KP index is updated every 3 hours. The AP index is averaged only once a day, every 24 hours. So it's quite possible that you could have a high K index and a low A index, because that hasn't affected the A index just yet. So I generally just ignore the A index when we're talking about predictions, and talk about the K index or the KP index. Because as I said, this updates every 24 hours. So I've had people say to me, this is weird. We've got a KP index of 6, and which is really unsettled, but the A index is only about 15. Why? And I said, well, this is why. That will update. You'll see it tomorrow, but it won't update for another day. So I think it's better to use the KP index, which is 3-hourly update. So you're more likely to see current conditions. With the A index you're not seeing current conditions, you're seeing conditions as they were 12 or 24 hours ago. So what do geomagnetic disturbances do to HF? Well, generally a high KP index means a lowering of the maximum usable frequency and bad noisy conditions. We can see the MUF gets knocked back quite badly. And you may find that, I mean, for instance, we've recently had quite a lot of propagation on 10 meters. If we suddenly had a high KP index because we were hit by plasma, you may find that 10 meters closes down, and that you have to go down lower in frequency to work around the world, if you can work around the world at all. Paths that go through the poles are most affected, but north-south paths that go over the equator generally are not so badly affected. So it's polar paths that are more affected. And also you can get a situation with the KEP index, just as it's rising, you get what we call a pre-auroral enhancement, and we find that the MUF goes up. So if you're ever in a situation where you're suddenly finding fantastic conditions on 10 meters and you think, oh, this is brilliant, make the most of them, because it may be that as a just big disturbance about to turn up, and it's going to kill the bands for you. They're very hard to predict. It's very hard to predict when you're going to get an enhancement and when you're not. But there we go. And so the solar wind speed can vary dramatically, but it's typically in the range 400 to 600 kilometers per second. So geomagnetic disturbances, not really good for HF. We prefer to have much, much quieter bands. So basically, we want to see a high solar flux index and a low KP index. That would be the best in terms of conditions. Now, CMEs. We talked about coronal mass ejections. There is a prediction engine on solarham.com. As you can see, you have to click the button to get it running. But this is kind of NASA's view of how a CME works. If you think of the sun as like a sprinkler, garden sprinkler, it's throwing out plasma all the time as it's rotating. So you end up with these sort of curved effects. So this is an attempt by NASA to try and work out what's going to hit us first. And if you can go and have a play with this at solarham.com, but it shows you the likely time of the effects of the CME hitting stereo A spacecraft and Earth. Again, the same again. Both the density of the plasma and the radial velocity. So you can see here that at this point it's gone up, the velocity has gone up, and as it's hit the stereo ahead spacecraft. So it'll then impact the Earth slightly after. So the stereo spacecraft are quite useful to us as a warning of what's coming. You know, it gives us maybe an hour or so's warning of what's actually going to hit the Earth, which is useful. You know, before we had any satellites at all, we were really reliant on luck, I think, more than anything. And I do know that Inmarsat, I was working for them at one point, and they keep a very close eye on the space weather conditions, and to decide whether they want to rotate the solar panels on some of their spacecraft so that they're less likely to be hit by material coming off the sun. But they worked out that the amount of fuel they use to rotate the solar cells, you know, probably made up for, or didn't make up for, the loss of the solar cells. So there's always this constant battle of, do we try and rotate the solar cells out of the way of the solar wind, or do we just let it hit it and take the damage that happens? It's interesting. So you can get an update on the future solar flux indices and A and K indices, both from NOAA, but these are both from NOAA and the USAF. I don't know. Yeah, you can't see. There's a URL at the bottom there. You can't see it because it's too light a color. But if you search for NOAA SWPC, the Space Weather Prediction Center, it will take you to this site, and you can download it. So we've got a 27-day outlook of the 10.7 centimeter radio flux and geomagnetic indices. Also, the United States Air Force do a separate one looking at the 45-day AEP index and the solar flux index. So by comparing these two, you can get an idea of what's happening, and this is how we kind of predict what's going to happen the next month. It's been terrible recently. It's not been very accurate at all. I freely admit that. But so if we say in GB2RS that, next week we expect the solar flux index to be about 130, you can guarantee it'll be about 115. Or if we say it'll be 105, it'll be 130. They're not terribly accurate, but you know, that's the way it goes. The Met Office have a space weather division. I've spoken to them about could we have some of their predictions, but they only predict 4 days out. So they don't do the following week. So we've begged them to try and come up with something a little bit more reasonable for us anyway, but we've got nowhere with it. So we have to use a number of tricks to get around this. One trick is to look at the sun rotates about every 27 days. So if you've had bad conditions 27 days ago, there is a chance that you'll probably have bad conditions coming up again. So that's one trick we used to look at what happened 27 days ago. And try and work out whether it might happen again. And also just looking at the sun and using the stereo head spacecraft to see
if there are any sunspots coming around, and trying to work out at what time they will be there. The coronal holes come and go, but if there's one of those rotating into view, then if I allow 2 days for it to get central, then allow another 2 days. So that gives us a 4-day advance notice that there may be a high K index, and that's how we do it. So it's tricky, but it's not easy. Now, the solar wind can be measured via spacecraft. This is from SolarHam again, and this is the real-time solar wind for the last 3 days. And you can see we've got the BZ at the top there. So you'll see that trace in red is going positive, negative for quite a few days. And this is typical of what happens. You know, the frozen magnetic field isn't static all the time. So what we're looking for in terms of trying to work out how bad things are going to be is high speed, definitely high speed, and increase in density and temperature as well. And then finally, BZ bit pointing south. And that's a good indication that things are not going to go too well. So that's how we do that. And that's a pretty typical sort of display that you get there. As you can see, the speed of the solar wind went from 400 kilometers per second up to more than 500 kilometers per second in less than a day. But meanwhile, the density went up, and the BZ was going up and down, up and down, up and down, which is pretty typical. So trying to predict whether that's going to hit the Earth or not would be very hard indeed. So let's just talk about this BZ again, or interplanetary magnetic field. This is a kind of a graphic looking at the Earth and the solar wind coming in. Where these two meet, we call that the magnetopause. And that's where we really want to know whether the BZ is pointing north or south. As I said, if it's pointing north, the material coming in off the plasma coming in on the solar wind will probably be deflected away from the Earth. If it's pointing south, it'll probably hit the Earth. What happens is that the plasma, the BZ is pointing south, gathers at this point called a neutral point, and we get something called magnetic recombination, and the stuff pours back into the poles, which is why we get an aurora. And I mean, if you visit Iceland, you can see the aurora with a KP index of about 2. I've done it. Whereas if you're in Norfolk, people on the North Norfolk coast, if you get a KP index of about 5, you can just about see an aurora on a camera, but you won't see it with the naked eye. You know that you have to do quite a long time exposure to see the aurora. But that's what you need to look for. So if anyone wants to go on holiday to Iceland to see the aurora, do talk to me, and I'll let you know the best times to go. I won't go through the whole story now, but I went twice to see it. The first time in January, and we froze to death and didn't see anything, and went back in April and did see the aurora. And I've got some fantastic pictures. But yeah, Iceland in January is not a pleasant place to be, believe me. It's cold, which I think the trick is to see what the place is called. Iceland, what do you expect? There we go. So the sun's magnetic field said isn't confined to the immediate vicinity of the sun, and a solar wind carries it throughout the solar system. They have aurora on Mars and Saturn as well. And the Earth's magnetic field and the interplanetary magnetic field come into contact at the magnetopause. And so if the Earth's magnetic field and the IMF point south, we say that there's a southward BZ, and that partially cancels the Earth's magnetic field at that point, and it comes into the Earth's atmosphere, or the ionosphere. So a southward BZ, this is what we mean by southward BZ, heralds widespread auroras. And in terms of geomagnetic storms, they are generally more prominent on the downward part of the solar cycle, just past solar maximum. So I think we had solar maximum about 2001 or 2002. And you'll see that 2003 there, we had an awful lot of magnetic storms. So in other words, we've got a lot more coming. If the next maximum is going to be 2026, then maybe 2027, 2028, we're going to have a lot more magnetic storms. So we expect a lot more disruption. Okay, we need to talk now about critical frequency and maximum usable frequency. What the critical frequency is if we fire a signal directly up, straight up into the ionosphere, the critical frequency is what's the frequency, the highest frequency, where it gets reflected back down or refracted back down again. And we can measure that with something called a digisonde or an ionosonde. And this is a plot from the Chiltern ionosonde. And you can see here that the frequency goes up, and this is the height, virtual height of the ionosphere. And you can see at this point here, you see it just stops. We'll just look at the red one for now, it just stops. So the critical frequency there is around about 7.5 megs, I think. And if you come over to this side and have a look, it will tell you what the critical frequency is. So FOF2, which is the critical frequency, 7.3 megahertz. You'll also notice there's this green strip here, which has gone a little bit higher. This is because any radio wave that enters the ionosphere gets split into two waves. We call them the ordinary wave and the extraordinary wave. And you can see the extraordinary wave has a slightly higher critical frequency than the ordinary wave. So that's the extraordinary wave is there at about 8.1 megahertz, and the ordinary wave is 7.3. We generally talk about the critical frequency being the frequency of the ordinary wave, but it just shows that it's not a clear cut as you think. There's an amount of radio energy that comes back down again from the extraordinary wave, not just the ordinary wave. But this is a digisonde plot from Chiltern, which is the Rutherford Appleton Laboratories digisonde. It doesn't appear to be working at the moment, which is why I've been saying to people, use the Fairford digisonde information. But we can tell a lot from this, so they're not so easy to read. But if you look along the bottom here, you'll see that we say for a distance of 3,000 kilometers, the maximum usable frequency is, on that day was 25.4 megahertz. But over 100 kilometers, it was only 7.9. So you can see that as we get further and further away from where we are, or as the distance increases, the maximum usable frequency goes up. And so this is useful information that tells us what sort of frequency we're likely to use over different distances. So over 800 kilometers or 500 miles, so the maximum usable frequency there is 10 megahertz. So this is all useful stuff, but these are a little bit tricky to read. So Jim Bacon, G3YLA, we were talking over a drink in the pub once, and he basically said, oh, well, I think we could turn this into something a little bit better. So he came up with something called PropQuest. And PropQuest is, it takes the data from Chiltern and Fairford and Daub and plots it. So now you can see immediately from this what the critical frequency is. It's 6.75 megahertz there, which gives us a maximum useful frequency over 3,000 kilometers on that day of about 25 megahertz. And you can go and look at PropQuest right now, and you'll see that a typical plot starts off quite low here, and as the sun rises, the critical frequency goes up, and the maximum usable frequency therefore goes up. And then as the sun sets, it goes back down again. So which is why 10 meters isn't open in the evening. It's a daytime band. So at the moment, with the way things have been going, this maximum usable frequency plot has been going up above about 30 megahertz during the day. Around about lunchtime is the point where you get the highest. So this is a useful tool that PropQuest has been made. It was actually programmed by people who worked for WeatherQuest, which was Jim's company. So they called it PropQuest for that reason. But I recommend you go to PropQuest and have a good look, because it's a very useful tool that will tell you why you can work as far as you can. We'll also tell you other things, like people say, well, how come I can work somebody 500 miles away on 80 meters, say, but I can't hear somebody just down the road? Well, this explains it, because to work somebody down the road, your signal's got to go straight up and then straight back down again, or near vertical incidence skywave propagation. But over 500 kilometers or 800 kilometers, 500 miles, that you're going out at a much lower angle. So you can, the frequency, comes down, or sorry, goes up a little bit. So 8.17 megahertz. So this is why you can sometimes hear lots of Europeans, but you can't hear anything around the UK. Of course, the critical frequency is too low to support near vertical incidence skywave propagation. Good. So we put it all together then, and we can use programs. Years ago, you used to have to run a program on your computer, mainly PC, but now it's all online. So people like Yari, OH6BG, and James Watson, I can't remember his call at the moment. He's got a Saudi Arabian call and a British call, but they've basically put these things online so that the programs are actually online now. So you can go on vocap online and you can call up a map of the Earth, point your pointer where you are, put the other one where you want to work, and it will come up with a plot like this. So this is Norwich to New York, I think. And you can see that we've got this lovely plot here. And this explains things quite nicely. You can see there that as the sun rises, the maximum useful frequency goes up and up and up. And it peaks at about 3 o'clock there, 1500 hours. And then it falls back down again. So that's a typical plot. And then as you get to nighttime, you'll find that the maximum useful frequency of that distance is usually about 10 megahertz or even lower. So this is a great way of working out the best band to work, different parts of the world. So for example, if you wanted to work New York on HF on 20 meters, I would start looking there at about 11 o'clock, and it will start to peak around about 2 o'clock to 4 o'clock, and then it will go off again. Likewise, if you wanted to work 10 meters there, you could see that you've got 12 o'clock, maybe 1 o'clock. By 2 o'clock, it may close down again. These charts are produced by vocap online. So go and have a play with vocap online. What you're looking for is the REL SDBW SNR option. That's reliability, signal to noise ratio, and signal strength in decibel watts. It's an awful term, but that's the one you need to look for to get one of these charts. So once you've got your pointer on where you live and the place you're trying to work, just look for that one down the bottom, click it, and you'll get a chart like this. So this is a good chart. So it shows you during the day why you can't work New York on 40 meters. It's below, or it's above the lowest usable frequency. In fact, the lowest usable frequency on that path is around about 10 megahertz during the day. But then at nighttime, it shows you why you can't work them on 28 megahertz, but you can work them on 40 meters. So it's a great tool for working out the best time and frequency to work different parts of the world. To give you another example, this is using PROPI, which is the other program that the Propagation Studies Committee worked on. Now, vocap online, vocap is quite an old program now, and basically the ITU said we want to come up with a different version, a newer version, and so they did their own research and they came up with something called ITU-R HF Prop. It's an awful term which hard to remember, but ITU-R HF Prop, and basically PROPI is the online version of ITU-R HF Prop. So James Watson took the program and gave it similar sort of usability as vocap. So if you search for PROPI or soundbytes.asia, you'll come up with something like this. So again, here we go. I put the TX pointer on my home, and I put the other one over in Wyoming, because I was trying to work Wyoming for my work to all states. And you get a chart like this. So again, it shows you that maybe 4 o'clock in the afternoon, I can't read what that says, that 1600 hours, 4 o'clock in the afternoon on this particular day, maybe 21 megs, maybe 18 megs would be the best time to work here. In fact, I worked Wyoming on 18 megs at 4:30. So it just shows you, if you want to work a particular station, be it a de-expedition or a certain place in the world that you want, this is the best way to do it, because it will show you absolutely the best time to work the world. So this is, as I said, PROPI, and it's at soundbytes.asia, and the other one is vocap online. Now, just one final thing then. With Bradcom, we have monthly propagation charts that are produced by Gwyn Williams G4FKH, and they're typically like this. This is one from 2019, so not an awful lot was being workable because the sunspot number or solar flux index was so low. But this was okay, but this is based on 100 watts to a dipole. And so if you've got a 400 watt linear and you've got a step IR at 100 feet, you're going to be able to do an awful lot better than this. Likewise, if you're a foundation license holder, you've only got 10 watts to play with and a bit of wet string, you're not going to do as well as this. So we've been trying to work out what would be the best way to adapt the RADCOM charts so that they were more useful for everybody. We came to the conclusion that we can't. So what we did is we put them online. So now you have two choices with the RADCOM charts online that allow you to choose the mode, power, antennas, and they will give you a chart specific to you. So the VOCAP charts, go VOCAP online, or if you go to rsgb.org.uk/VOCAP, it will take you to this page. So you can see, you can select your mode, and it will do FT8 as well, how much power you're running, and your antennas. You get a choice from dipoles to Yagis at 80 odd feet or whatever. Then when you're ready, you just hit the button and it comes up with a chart like this, or the chart on the left. So as you can see now, this shows you, if you're trying to work Moscow, what band would be the best band to work for each hour of the day. So it's similar to the charts that are in RADCOM, but it gives you an awful lot more information. So you've got 26 locations around the world like this, and you tune it to your station. So depending on what power and what antennas you've got, you will come up with a set of charts for the month. But this is something we just can't do with RADCOM. We haven't got enough space to do it. We just, trust me, we've talked about it, but just not going to happen. And PROPI, which is the ITUR HF program, James Watson has done the same thing. So the later programs, later to VOCAP, go in, you get a similar pattern. So you say, oh, I've got so much power, I'm running FT8, and I've got a Yagi at 80 feet or whatever. And it will come up with charts like this. So you can see instantly the best time to work, best time to work around the world. So the URLs that you need are rsgb.org.uk/VOCAP and rsgb.org.uk PROPI. And they will both give similar answers, but both, I mean, I don't know which is best. We're having some research done. That's Gwyn Williams is saying that he says that the ITUR HF prop is more accurate than VOCAP, but it remains to be seen. We'll have to see. To be honest, if you're going to use either tool, that's a bit better than guessing anyway. But we'll have to see. Good. So finally, putting it all together then. So for best conditions, we want a high solar flux index. And if it's been up above 150 for a few consecutive days, that's about as good as it gets, quite frankly. Anything below about 100 is maybe poor conditions. Anything above 100 is marginal. And anything above 200 is going to be fantastic conditions. And I think the best we've done so far is about 150. I think it was 115 today. So it's borderline as to whether 10 meters would open up. Now, on the other side of the chart there, we've got the K index. Has to be low, so maybe below 2 for the best conditions. So best conditions, you want a high solar flux index and a low K index, preferably below 2, 1 or 0. That's what you need to look for. If it goes the other way, if you've got like a solar flux index of 50 and a K index of 9, you're not going to work anything. You know, the conditions are so bad. But so really, that's just about the one I want to finish on. So we're looking for a high solar flux index and a low KP index for the best HF conditions. So finally then, there's two propagation YouTube videos that are available. They were originally put together for clubs, but they're now been made publicly available for everybody. So if you search for Understanding HF Propagation, that's a 40-minute video that I put together. And if you want to understand VHF propagation, that's I think it's about a 25, 30-minute video that was put together. I put it together, but it was actually written by G4BAO, John G4BAO, and you're more than welcome to view those. So the two programs that you know, we recommend people, if you're absolute beginners, it's a good starting point anyway. And the Understanding VHF Propagation one has got examples of auroral propagation on it, meteor scatter, aircraft scatter. So it's quite good. So if you've never heard of what an auroral signal sounds like, you will now. Anyway, on that, I'll end this presentation and put it back to open up to questions. Right now, where do we go? Got to switch off my screen, haven't I?
I've done it for you, Steve.
Oh, thank you. Yeah, brilliant.
Well, thank you very much, first of all, for a fantastic and informative talk. That was great. I really did enjoy that. I thought that was really, really informative, and it's quite a lot that goes into the study of propagation. I had no idea, to be honest, but no, that's fantastic. So if anybody's got any questions, if they're wanting to unmute themselves and ask Steve a question, then feel free.
I think they're all asleep.
Yeah.
Well, it's Peter G3MLO. Do you hear me?
Yes, I can hear you.
Jolly good. Well, thanks first of all, Steve, for a very informative lecture. And you can see from my course line, I'm up in age, been around a few years. And I must admit, I've not fully ever understood how to predict the state of the bands. Obviously, I know the basics, but I think there's a lot more out there now than there was when I studied it in detail. So it's given me an eye-opener to what to look for, and I thank you very much for all of the URLs and for your work that you've done. So again, they always say you're never too old to learn, and it's been a good lesson tonight for me personally.
Well, I'm glad it's useful. Excellent. Yeah. I wrote a book for RSGB as well, Understanding HF Propagation, which is I'm not pushing it by any means, but it's a good basic guide, I think, to HF.
Yeah, thanks for that.
Yeah, good.
Yeah, I can endorse that. I've read your book, Steve. So
Oh, good.
Yeah, this is sort of step on from that, but it's going to take a bit of time to absorb all the information and compare it, isn't it?
Yeah, helps if your microphone keeps working as well, but I have no idea why that kept cutting up.
It's yeah, it's one fact we can all agree on. Technology always lets you down when you most need it.
Absolutely.
Thank you,
Thank
Steve.
you for a great presentation. It was very understandable.
Good. Thank you. When I give this talk in public, normally there's at least 2 people fall asleep.
Yeah. Thank you, Steve.
Okay. Good. Any more
Does anybody-
questions?
Any
Yeah,
more
I've got-
from anyone?
Yeah, I got one more question. This is what I ask everybody, basically. Long delayed echoes. Now, I've heard these over many, many years. Nobody has an explanation. Is there any research in depth going on about this phenomenon?
That's a very, very timely question. We're basically about to start a new long delay echo program that will look at them. That we've been talking about it for years, but Peter Duffett-Smith is an ex-physics professor, doctor from Cambridge University, and he's decided to go ahead and do it now. So he's devising a method of looking for long delayed echoes using a kind of beacon system that will transmit a series of tones at the same time that it's listening for the other kind of it will do it every 10 seconds and listen for the other 9 seconds for anything that comes back. We're not thinking that we're going to be hearing loads of long delayed echoes. The current feeling is that they're a very, very rare occurrence. And the likelihood is that it's something to do with the radio waves that are getting trapped in a kind of a loop, if you like, or almost like a waveguide in space.
Yeah.
That's bringing them stuff back. I mean, if anybody's never heard of LDEs, you can hear a round the world echo with a very short delay on it when the conditions are right, when we've got a very solar flux index and you can transmit and you've got a beam. If you transmit, you'll likely hear your signal twice with a slight echo on it, as one half goes around one way around the world and the other half goes the other way around the world. But an LDE could be up to maybe 5, 10, I think 22 seconds is one report we've heard as well. So he's going to start this, I think it's next year. But the reason we've kept quiet about it is we don't want anyone interfering with it, because if somebody was listening for this thing, recording it and playing it back, we'd think it was a long delayed echo and it was just somebody messing about. So we're keeping the frequencies that are going to be used very, very quiet indeed. And I think it'll maybe run for a year or two and we'll see what comes out of it.
Yeah, that's very interesting. I mean, the last one I heard, funnily enough, was on 40 meters and I managed to record it. And
I think my
it was
sound's gone again. Let's have a look.
No.
Yeah, it has.
No, you're right. To me, anyway.
Yeah, receive sound went that time. I don't know why.
Yeah, so it was a delay on a 40-meter signal. I was working with an American who had stacked 40-meter Yagis, and I'd had a contact with him and I was listening to his the next QSO, and I recorded the delayed echo, which was 2 seconds.
2 seconds,
and, yeah. And I thought maybe it was even a reflection off the moon, because I did not with E&E at one time, and that was about 2 seconds. But it's something I've heard quite regularly, and in fact, if you sit long enough and just send, Morse code, dots or whatever, you can, in fact, hear your own signal. But you need good switching on your radio, obviously, between transmit and receive.
Yeah.
In a modern rig, that's possible. But yeah, it's sort of fascinating.
Yeah. Yeah, it's something that's been on the back burner within PSC for about 5 years. One of the members said he was going to study it and never found one. And we said, look, we've got to be a bit more scientific about this. So that's why Peter's taken it over and is coming up with this beacon idea. But I think it's going to need a lot of power. This is not a QRP project at all, but we'll see what he comes up with anyway.
Yeah, interesting. Yeah. Thank you.
Good. Any more for any more, as they say?
I'm done.
No, I think that's about it, Steve. I think you've got, to be fair, I think you covered so much that it's been really invaluable.
Okay.
It's good. I'm going to be interested in rewatching the video and grabbing a copy of your book as well and getting it nailed down.
Okay, I'll make a copy of the presentation right now. What format do you want it in? PDF or as a PowerPoint?
Yeah. PDF's fine. PDF's fine.
Okay,
yeah,
I'll do it right now and I'll send it to you.
Yeah, thanks, Steve. I appreciate that. Thanks very much.
Good. Okay.
It's been a really good night. I've enjoyed it. Thank you.
Excellent. Thank you. Well, thank you for inviting me. I'd never heard of you before, so it's quite interesting.
Great. Cheers, Steve.
Good. All right. Cheers then. Bye-bye.
Thanks.
Yeah, cheers,
thanks, Steve.
Bye.
See you soon.
Bye.
Bye, John.
Cheers, Steve.
Bye, Emily.
Bye, Roger.